Hi guys, welcome to Unit 2 of Math 107, and we are going to start in Chapter 5. Today we'll be covering the notes for Section 5.1 Part A, and we will begin our discussion right now. So let me share my screen so we can start with the notes, okay? Okay, so in Chapter 5, we're going to begin by discussing the concept of primes, composites, and divisibility. We're not going to go all the way into the test for divisibility today, but we are going to talk about what divisibility is and what it means and how that has to do with factoring. These are all important concepts because, as you know, as a teacher, you're going to be teaching these concepts, number one, pretty much as we're going to be discussing them today. But they're also building blocks for things like working with fractions, factoring polynomials, so on and so forth. So these are all important skills to have under your math belt. All right, so let's begin with primes, composites, and tests for divisibility. So today we're going to talk about, let's start with primes and composites, and let's start with a couple of basic definitions. Okay, so our definition is definitions for what prime is and what a composite is. So a prime, okay, is defined. Let me highlight that better. There we go. Primes are defined as a counting number that has exactly two factors. That's the important part right there. And those two factors are right here. They are 1 and itself. And I'm going to make this a little bigger here so we can read more carefully. All right. So here are some examples. We have, for example, the number 2. It is a prime because it only contains 1 and 2. Remember that factors are the two numbers that can multiply together to give you, as a product, the number you're discussing. So if the number we're discussing is 2, the factors of 2 are two numbers that will multiply together and give you 2. There are only two, 1 and itself. Okay, so it fulfills the definition of a prime, which is that it's a number that only has two factors, 1 and itself. Okay, you can see other examples here. We have 3, which also only has 1 in itself. We also have 5, which also only has 1 in itself. Now, there is an infinite number of prime numbers, just like there's an infinite number of counting numbers. Okay? Now, what are composites? Well, it's kind of like in the alphabet. If you'll remember, in the alphabet, okay, we have 5 vowels. A, E, I, O, U. And then all the rest of the letters of the alphabet we call consonants by virtue of the fact that they're not vowels. Well, the same thing is true for primes and composites. Primes have a very definite definition. Composites are basically all the other numbers in counting numbers that do not fulfill the definition of prime. But we do have an official definition if we want to use that. A composite number is a counting number that has more than two factors. But you can see that the definition is, in fact, the opposite of what a prime is. So if you know what a prime is, then by default you'll know what a composite number is. Because if a prime number is a counting number that only has two factors, 1 and itself, then a composite number is any number that has more than those two factors, is therefore not a prime, and by default it is composite. And you can see here are some examples. We have 4, which has 1 and 4, but it also has 2 and 2. So right there, just by having one extra factor, the factor 2, it stops being a prime and becomes a composite. We have 6 that has 1 and 6 and 2 and 3. So there you go. Now it's composite because it has more than itself. And the same thing is true for 10, 1 and 10, and 2 and 5. Okay? Now, a couple of things to note. Please note the following. Okay? 2 is an even number, and it's also a prime number. Okay? So there is a misconception, and your students will often have this misconception, and that is that prime numbers are all odd, and that is not the case. 2 is the first prime number in the counting numbers set, and it is an even number. But as you saw here, it is also a prime number because it fulfills the definition of a prime number, that is, being a number that only has two factors, 1 and itself. Okay? So, 2 is a prime number, but it is also even. And then another misconception, is about the number 1. Number 1 is an odd number. So, a lot of your students often want to say that the number 1 is a prime number. However, here's what's important to note. The number 1 is not a prime number, but it is also not a composite number. So the number 1 is odd, and it is not prime, and it is not composite. So it's neither prime nor composite because the number 1 does not fulfill either definition. Okay? So the number 1 kind of stands out all by itself. It does not fall into the box for prime numbers. It does not fall into the box for composite numbers. It falls into neither. It stands alone as its own entity. Because if you recall, the composite says that the number must have more than two factors. The number 1 does not have more than two factors. It has one itself. To be a prime number, it must have two factors, 1 and itself. And the number 1 does not have that. It has only itself, which happens to be 1, but it has no second factor. So because it cannot fulfill the definition of a prime number, the number 1 cannot be considered prime. And because it cannot fulfill the definition of a composite number, the number 1 cannot be considered a composite number. It stands alone by itself as an exception to both. But all other counting numbers will either fall under prime or under composite. Now let's talk about how we can kind of make that determination. There is a algorithm that was developed called the Eratosthenes, the sieve of Eratosthenes, and this sieve of Eratosthenes is defined as an algorithm that is used to find prime numbers. This here is the process of doing so, okay? But I'm going to take you through it in a minute. Let's read through what that process is. First of all, you skip the number 1 because, as we said, the number 1 falls into neither prime nor composite, so we have to skip it. Then you begin by circling the number 2 because that is the first prime number. After circling the number 2, every other second number you're going to cross out until you get all the way to the end of the parameters that you've set. In the case of our example, we are going to look and see how many prime numbers we can find up to, I believe, like the number 45. But you can basically keep going as much as you want. You can use the sieve of Eratosthenes to find the first 100 prime numbers or the first 50 prime numbers. It just depends on the parameter you want to set. But you would start by taking the number 2, you would circle it and cross out every second number until you reach the end of the parameter that you have set. Then you go back and you circle the number 3, so that's step 3. And this time you're going to cross out every third, as you can see here, number. Then you would go back and cross out the next prime number that you at this point would have been identified, which happens to be the number 5, and you would cross out every 5th number, and so on and so forth until you've done all the numbers within the parameters that you've set, and you now have circled all the prime numbers, and all the composite numbers would be crossed off. So let's do that as a practice. Okay, And I have a little example for us to look at right here. Okay, so according to the directions, we skip the number 1, we circle the number 2, and now we cross out every 2. So we count 1, 2, cross it out. 1, 2, cross it out. 1, 2, cross it out. 1, 2, cross. 1, 2, cross. Sorry, let's do that again. Here we go. 2, 2, 1. Oh, that's where we made our mistake. My mistake there. Let's try that again. So 1, 2, cross out. 1, 2, cross. 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 Cross. And I'm going to keep doing this only because I know it's a little tedious, but you need to see how this works. 1, it does show up on the test for this unit. 2, because you need to notice that sometimes some numbers will get crossed out multiple times as you are following through with this algorithm. Okay? 1, 2, cross. So I want you to have a visual for it. So bear with me as we do this. I know it's a little tedious, but bear with me. In this case, and then we run out. As you can see, I cannot do any more. So now we would go back and we would circle the number 3. And now we would count every third 1 and cross it off. So it'd be 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3. And you notice that every once in a while we are landing on a number that was already crossed out, right? 1, 2, 3, cross. 1, 2, 3, cross. And we sometimes are catching ones that weren't crossed out before. 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3, cross. Oh, sorry. I think I skipped one again. There we go. Okay, so we left at 33. 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3, cross. 1, 2, 3, cross. Okay? And now we go on to the next one that hasn't been crossed off. In this case, it's the 5. All right, so now that we circle the 5, we're going to cross out every fifth. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sorry about that, guys. It's just really sensitive down here. 1, 2, 3, 4, 5. Okay? And the next one that you have is the 7. At this point, you should notice that we are no longer crossing out any new numbers, which means you have basically identified all the prime numbers within the parameters of from 1 to 45. But let's just check it out. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, and we run out. So you can see that at this point there are none left, and we can confidently say that the rest of these numbers are indeed primes. And these are all the primes to be found between the number 1 and 45. Okay? And you could expand this if you were going to do it between the numbers 1 and 50, between the numbers 1 and 100. But those are the steps that you would follow so that you could use the algorithm of the sieve of Erastes, okay? And by doing this, you would, in essence, find all the circled numbers would then be the prime numbers, okay? And that is one way to identify them the first time around so that you can spot them, all right? Now, once you know what a prime number is and you've been able to identify it, there are ways to work with them. And the way that is most often taught is by using factor trees, okay? Now, factor trees, something important to note, you can only use factor trees for composite numbers. In other words, we use factor trees to find the prime factorization of a composite number. We do not use factor trees to do anything with prime numbers because you cannot factor prime numbers, as we already talked about in the definition. They have only two factors, 1 and themselves. But we can factor composite numbers. And we can do so, and here's the important part, composite numbers can all composite numbers can be expressed as the product of smaller numbers using factor trees. Now you already know that. You can take any number, come up with its factors, and express that number by saying it is the product of these smaller numbers that you multiply together. But when we're doing factor trees, we are interested in finding the factors that multiply together to give us the composite number we're talking about, but all of those factors that we're looking at are prime numbers. And prime factorizations can be very useful, as you're going to see later on, because it is a very useful and efficient way of finding the greatest common factor when you're talking about fractions and how to work with them. It is also a very useful and efficient way to find the least common denominator. So it is important to be able to do a prime factorization. So here's an example, okay? And you can do a prime factorization basically by starting by any two factors that exist in that composite number. But what you should note is that no matter which two factors you choose, if you do it correctly, you always end up with the same prime factorization. So you can see here that we started with the number 60 as our composite number. And the first time we factor it into 6 and 10, okay? Now, neither 6 nor 10 are prime numbers, which means we have to factor them further until we only have prime numbers that are multiplying together to give us 60. So 6 can be factored into 2 and 3, both of whom are prime, so we hold on to those. And 10 can be factored into 5 and 2, which are also prime, so we'll hold on to those. So it turns out, and I'm going to go ahead and erase this and just highlight it so it's a little easier to see. It turns out that the prime factorization for 60, okay, is 2, 3, 5, 2, or the way we would write that, expressing it using exponents, as you're going to see here, is that we would write it like this. 2 squared, because it appears twice, and then times 3 and 5, times the 5. We usually put it in increasing order, okay? But that's because we started with the factors 6 and 10. Now, what if we took that same 60, but this time we started with the factors 5 and 12 that also happen to multiply and give you 60, okay? We could start there. We keep the 5 because the 5 is prime, but that 12 isn't, so we have to break that 12 down. We break that 12 down into 3 times 4. We keep the 3, again, because it's prime, but that 4 isn't, so we need to break that down. When we break that down into 2 times 2, both of those factors are indeed prime. So once again, we have the full prime factorization. And what you should notice is that prime factorization is the same as before. It is 5, 3, 2, 2, or as we wrote it here, 2 squared times 3 times 5. And if you look here at our third example, it's the same thing. This time we decided to go with 3 times 20 gives us 60. We keep that 3 because it's prime, but that 20 isn't, so we break it down into 2 times 10. Keep that 2 because it's prime, but break down that 10. Take that 10 and break it down into 5 times 2. Can keep both of those because they're prime. And once again, we have landed on the exact same prime factorization, which is the 5 times 2 times 2 times 3. So you see that all of them, regardless of where we start, leads us back to the same prime factorization. And that is because of the following theorem. Okay? The theorem states that all composite numbers can be expressed as the product of prime numbers in exactly one unique way. Okay? So all composite numbers have one and only one prime factorization. Now, one of the ways that I like to think about these factor trees when I'm trying to break it down is you can take any composite number you started with, like we did with this 60, and you can break it down to the first two factors you can think of that multiply as 60. But after that, what you should do is you should be hitting it with a prime number. When I say hit it, it means divide a prime number into that number that you're trying to break down and see if it goes in evenly. And the biggest hint that I always give my students is that whenever you're doing factor trees, almost always the prime numbers you work with are 2, 3, 5, and 7. Rarely do you have to go above those prime numbers. So I see the number 16, I think, well, it's even, so I can hit it with a 2. And I could go 60 divided by 2 gives me 30. So now I already know I have 2, which is a prime number. Now I've got to break down that 30. And again, I would say, 30, it's even. I could hit it with a 2, or I could hit it with a 5 because it ends in 0. And if I hit it with a 5, I'm going to get 5 times 6. I can hold on to that 5 because it's prime, and now I just got to break down that 6. Okay, so you usually use these to help you break down a number when you're trying to find its prime factorization. Okay? And like I said before, we use the exponential notation as a way to write the prime factorization more efficiently. Okay? Now, you just heard me talk about how when we're talking about prime factorizations, we think about what prime numbers that we know of can divide evenly into this composite number that we're trying to break down. And that's where we get into our conversation about divides. Okay? When we say divides in math, what we mean is that when we do a division of a particular number, it yields what's called a zero remainder, or sometimes you hear it spoken of as divides evenly into. Okay, and what we're saying is that the divisor, the thing we're dividing by, the thing that's being divided rather, is divisible by the divisor that we're dividing by. So we have the divisor A, which is the thing we're dividing, is divisible by divisor B, which is the number we're dividing by, and it is therefore, the number we're dividing by is therefore a factor of the number that is being divided because there is no remainder. And this means that if you would take A, it is definitely a multiple of B. So this is sort of the way we describe it, but it's easier to understand when you actually look at it. So let's look at this example, okay? If we have the number 15, that is the divisor A. That's the thing I'm dividing. And I divide it by 3. That is divisor B, or the thing that is doing the dividing. Because there is a zero remainder, okay, I know that 3 will go into 15 or divide into 15 5 times. Because this is true and there's a zero remainder, that means that 15 is divisible by 3 and that 3 is a factor of 15. Okay? So just as much as when we talk about that the factors of a number are the two numbers that we multiply together and it gives us that composite number, also, if a number divides evenly into that composite number, i.e., like when we're doing our prime factorizations, and there is a remainder of 0, then that number that we're dividing into our composite number is also a factor, okay? And it also fulfills this definition of what we mean by divides by into that obviously 15 is a multiple of 3. Remember that a multiple simply means we can take 3 and multiply it by something and we would get 15. And sure enough, we know that. We take 3 and we multiply it by 5 and we get 15. All right, so that's where we're going to stop today for part A of section 5.1. We will do part B of section 5.1 on Wednesday. But for today, this is section 5.1 part A. That is, and you do have homework number 9 that goes with it. It's already up on your taskbar. That homework will be due on Wednesday by 1 p.m. Wednesday, you will have another video lecture for section 5.1 part B and another homework assignment that will also already be up on your taskbar, and you will complete that by 1 p.m. on Friday. All right, guys, have a wonderful day, and I hope to see you on Friday at our live Zoom.